Well, saludos everyone and good morning. I'm Edgard Rivera-Valentín. So I'm going to give you already the big message here is maybe I found a radar signature related to the PSRs and related to ICE. We'll see. But for some context setting, I'm a member of the RASL survey team at APL. We have 3 primary science focuses, all of them to facilitate the future of lunar exploration. I'm primarily under the volatiles focus, and my specific task is characterize radar signature of icy regoliths. Now, if you know something about radar, you might be thinking to yourself, we know how water ice looks like in radar. And I would go, do we? Do we really? And sure, I'll concede that when we're talking about large volumes of water ice, sure, we know how that should look like. We have great examples on the Earth and a beautiful example over at Mercury. So I'm showing you here is an Arecibo S-band radar backscatter map in the SC, so same circular polarization as transmitted. And this is for Mercury's North Pole. I'm highlighting some of the main craters there, and you see they're really pretty, really bright. The other aspect for water ice is that it should have a high circular polarization ratio. It's not just high, the values should primarily be between 1 and 2. And so above the map, I'm also showing you a normalized probability density of the CPR distribution over the PSRs in Mercury. That was a lot of acronyms, I just realized. But note that the primary CPR values are between 1 and 2, which is exactly what's expected if the coherent backscatter opposition effect is what's causing the radar brightness. But if we then look over at the moon, specifically the lunar south pole, which is what I'm concentrating this talk on, and we look at the PSRs versus non-PSR terrains, we look at radar brightness versus CPR, first thing to note is those 2 lines there, cyan for PSRs and blue for non-PSR, they look very similar to each other. There's pretty much no difference. And the CPRs are all less than 1. Okay, so what gives? Where's my water ice? We have other evidence that there's water ice there. What's happening? And what I would say is that there's no large volume of water ice within the top meter of the PSRs in the lunar south pole. The other thing I would say is that the metrics that we're using to characterize and identify water ice, especially at the low volume fraction levels that might be in within these PSRs, should not be just radar brightness and CPR. We need to look at other radar properties. And so a framework that I've been leveraging to look at the signature of water ice is what's called circular backscatter component analysis. And I say what's called, I'm actually naming it that. The authors didn't give it a name, but I feel like this is a pretty name for it. It gives you a nice acronym too. The authors are Ann Verkey and Sriram Bidavadasu. They published this in JGR. And what they say is, let's not look at CPR, which is a ratio of the same circular to the opposite circular polarization. Let's look at them separately. And in fact, when I apply this over to Mercury, you look at the plot here with CPR versus incidence angle, where blue is the PSRs and the black is the non-PSR terrain. When you're just looking at the CPR, good luck identifying a difference between those 2 things. It's because at high incidence angles, you naturally also get to high CPR. But when you look at them in this SCOC plot, suddenly those 2 populations are distinguishable. Now, the authors go further than this. They don't just say, look at the pretty plot. They say, do component analysis. So what they say is, consider a linear model and look at the components of that model. The intercept is related to the dielectric permittivity of the material you're zapping. The slope is related or inversely related to the diffusive CPR, not to be confused with regular old CPR, diffusive. CPR has a bunch of stuff folded into it. Diffusive CPR is just looking at the diffusive component of the backscatter. The extent of the line is related to the heterogeneity. So the extent is the line that best matches the overall variation in SCOC space. So if the line is short, most of the scatters are likely about the same size. If the line is long, then you have scatters or a bunch of different sizes. And R squared is the correlation between SC and OC. Basically, if once you backscatter, you're hitting the same thing, you're hitting the same dielectric contrasts, and those are producing the same SC and OC, then those are going to be correlated with each other. But if you're, let's say, a pretty flat surface, OC is your specular component, SC might have traveled through the regolith, hit a different dielectric contrast before coming back out, the thing that affected both are different things, and so it starts anti-correlating them. And so these are the 4 components that they suggest we look at, and that's what I did. I looked at those components for the lunar South Pole. So what I used here is mini RF S-band monostatic data. There's a mosaic that we have of the South Pole. Now, radar data is very viewing geometry dependent. It is context driven. You can't just take it without understanding what the local incidence angle is, what the phase angles were. You have to keep that into account. So a way to remove those biases is that I also use a slopes map, and I'm only looking at the flat part of the PSR. So I'm controlling for that viewing geometry. Okay, and then over those sections, I'm doing this component analysis. In these plots, now I'm showing you the distribution of those components for PSR, cyan, non-PSR terrain, blue, only over the same slopes. And guess what? Remember those first plots where they look the same? Look at the magenta. I found a radar signature related to the PSRs. They're actually coming out as unique signatures. The PSRs have much higher diffusive CPR than non-PSR terrain, and they also have a higher intercept value. Their magnitude and R-squareds are about the same, but those two values are different. And so that lets us know that the PSRs can be considered likely having rougher scatterers or weirdly shaped scatterers, and likely having a higher dielectric permittivity. Now, I'm not going to stop there because I still have about 4 minutes left. So the next step is, hey, I found two parameters over which the variation is unique for the PSRs. Let me now look over those parameters and see if I can start clustering and untangling a little bit more information. So to do this, I did a very basic type of clustering. So I z-score normalized both the diffusive CPR and the intercept. So now we're looking at variation in terms of standard deviations above the mean value. And then I did a very basic quad style clustering. So group 1, everybody's above mean. Group 3, everybody's below mean. And then group 2 and group 4, one is above, one is below. And then I mapped the PSR as cohesive units rather than the pixel scale. And just to give you some setting, because I forgot to put latitude lines on this, Los Tres Amigos, you see them there. They're nice and pretty. Blue group, right? Shackleton, right smack in the middle, yellow group. We're also seeing that some of the PSRs are falling into two groups. Amundsen has both group 1 and group 4. Cabeas has 3 groups, group 1, group 4, and group 3. There's a lot that can be done with this and a lot that I've already done, but not enough time to talk about this. But there's spatial coherency analysis you could do with this. Some of the groups actually look randomly distributed. Some of them actually are coherent and are following a longitude line, which I was like, that's super cute. And I'm continuing doing that work, but not what I'm going to show you today. You're going to see other stuff. We're going to now relate those groups to something other than radar. I know it hurt my heart doing it, but we're going to go there. I'm going to look at temperature and water equivalent hydrogen. And when we look at temperature, above is average summer temperature, below is maximum temperature. For the average summer temperatures, we're seeing that the group 4 and group 3 are leaning towards a bit higher averages, while group 1 and group 2 are a little bit lower. But for volatile stability, you actually care about the maximum temperature. So I'm going to focus on that. Group 1 and group 4, you see the distribution ends right about at 180 Kelvin, so they're constrained to be less than that temperature. The other two groups have this long tail that leads them to be above 200 Kelvin. Group 1 is also in both averages and the maximum temperatures leading to very low temperatures. Now what's interesting here is that group 1 and group 4, if you remember from that quad clustering, that's variation across the intercept. That's variation across dielectric permittivity. If we're looking for water ice, I should be looking and seeing something varying up and down through that. So seeing this correlation is interesting. And when I look at water equivalent hydrogen for group 1 and group 4, I'm seeing a bimodal distribution where one of the modes for both group 1 and group 4 are high and the other two modes are a bit low. So there might be local scale heterogeneities within the PSRs themselves. So that's also interesting. While group 2 and group 3 there is some assemblages for multimodal distributions, but they're all rather low. So super cool. There might be a link here. What is the take-home message? I don't see Clive Neal in the crowd, but on Tuesday, he was like, Ed, did you find me water ice? My answer is, give me like a couple more months and I might say yes, okay? But for now, I did find a radar signature that is unique to the PSRs. They are standing out. Those signatures, once I start teasing things out, they're correlated to temperature and water equivalent hydrogen. And the variation is what I would have expected going across up and down the dielectric permittivity. I need to do more spatial analysis work and modeling so that I can tell you at the end of the day, go to this PSR in this location, and that's where you will find water ice. With that, I will say gracias.